Hi, good evening everyone. My name is Torik Abilavan Kusuma with student ID number F1T02410098. So in this video, I'll be walking you through my final project, which is titled GPU Accelerated Chest X-ray Image Processing using CUDA and PySpark. As you can see at the top of this notebook, the goal of this project is to build an image processing pipeline that combines two parallel computing technologies. So PySpark for distributed big data processing and CUDA for a GPU accelerated image processing. Alright, now we're moving on to the datasets. Alright, so we start by mounting Google Drive where the dataset is stored. The dataset contains 1000 chest X-ray images. I can show you here. So there are 500 labeled normal and 500 labeled pneumonia. These are stored in two separate folders, and the total is 1000. Alright, now we get to the PySpark parallel concept. Where is it? Oh yeah, here. Alright, so I create a Spark session here. This is the entry point for all PySpark operations. Inside it, there's also a Spark context which handles the lower level RDD operations. Moving on to the map. Alright, so the first operation is map. Each image path is transformed or mapped into metadata. The file name, label, width, height, and mean brightness. This runs across all 1000 images in parallel using the RDD API. And moving on to filter. Alright, so I filter out images whose mean brightness is below a threshold. This is done using RDD filter through a Spark context. Next is reduce. Alright, so I aggregate across all images to compute total pixels, average image size, and average brightness, all done in parallel. That's how I use reduce. And finally, the SQL. So I register data frame as an SQL table and run queries using Spark Sessions SQL API. For example, counting images per label and computing average intensity per class. So all four operations have their execution time measured, so we can compare them at the end. Now we're moving to CUDA parallel concept, which is on section 7, I think. Yeah, here it is. So in CUDA, computation is organized into 3 levels. A grid covers the entire image. Each grid contains multiple blocks. Here we use 16 times 16 blocks, so 256 threads per block, and each thread processes exactly 1 pixel. Okay, moving on to section 7.1b. So here's the first CUDA kernel, histogram equalizations. So you should take a look at these lines. So this calculates the global positions of each thread, giving every thread a unique pixel to work on. And now, moving on to Gaussian blur kernel. This kernel handles Gaussian blur. Each thread computes a weighted average of its 5 times 5 neighborhood. And then we got to Sobel kernel. And this one is Sobel edge detections. Each thread computes horizontals and vertical gradients to find edges in the image. Each of these operations has both a CPU versions and a CUDA versions. We time both. Alright, so this is the results of the filter that we put it on. So each row is a different chest X-ray sample from left to right. The original image, then the result of histogram equalizations, Gaussian blur, and Sobel edge dissections. And we not only have normal here, we also have the pneumonia ones. And here we compare the CPU and CUDA outputs side by side. As you can see, the results are visually equivalent. The difference is purely on how fast they were computed. Alright, so now the most important part. The first table compares all 4 PySpark operations. This one. Map takes the longest because it reads and processes every image file. Filter and reduce are faster since they work on data that is already in the memory. SQL query is also efficient because of Spark's query optimizer. And now moving on to the second table. So the second table compares CPU and CUDA for each image processing operations, and we also compute a speed up value, which is CPU time divided by CUDA time. And also we have the chart for the comparisons here. So looking at the chart, CUDA is significantly faster across all 3 operations. The speed up is highest for Sobel agitations and Gaussian blur, because those operations are the most compute intensive per pixels, making them ideal for GPU parallelisms. And the result confirmed that GPU acceleration provides significant speedups for image processing. I think that's all from me. Thank you very much.